Welcome to Angles of Rotation, the second section in Chapter 13, our Introduction to Trigonometry. In this chapter, or this section, we're going to draw angles in standard position and determine the values of the trigonometric functions for any angle in standard position. Basically, what we're going to be doing is putting our angles onto a coordinate plane and identifying the vertex at the origin and determining the angles of the rotation from the initial side to the terminal side. These are the vocabulary words found in this section of the chapter. Last class we talked about trigonometric functions using acute angles and right triangles, and we set up ratios related to that. Trigonometric functions can also be evaluated with other types of angles. There are a couple things we need to learn first, and that is when we put an angle into a coordinate plane, we have what's called standard position when the vertex of that angle is pinned or associated at the origin, and one ray is along the positive x-axis or on the right-hand side. The initial side of the angle is the ray that is on the x-axis, and we call the other ray the terminal side of the angle, and that's where the angle ends basically in its rotation. We can see a picture on our next slide. When we're looking at these two pictures, one of them indicates a positive rotation. Rotating counterclockwise gives us a positive angle. We can see in here that our initial side is along the x-axis. This is our initial side right here. When we rotate from the initial side to the terminal side, as we do here, terminal side in red, we have an angle measure of 135 degrees for a positive rotation. In the same token, when we set up our initial side along the positive x-axis, so we put it in standard position, and we rotate in a clockwise direction to our terminal side, we are moving in a negative direction as far as rotation is concerned. The angle of rotation is formed by rotating the terminal side, keeping the initial side pinned in place along the x-axis on the positive side. If the terminal side is rotated counterclockwise, as we indicated in the last, counterclockwise, this is positive. And if the angle of rotation is clockwise, and that terminal side is moving clockwise, then the angle of rotation is negative. The terminal side can be rotated more than 360 degrees. So that's a key point to understand here. We can go around more than 360 degrees in this rotation. A 360-degree rotation starting at the initial side or at the positive x-axis, going all the way around and returning to the positive x-axis is 360 degrees. Halfway around would be considered 180 degrees. What we're going to do now is draw angles with the given measurement in our standard position. So we're going to draw an angle with the given measure in standard position. Letter A has an angle of 320 degrees. When we draw that angle, we find that we're moving in a counterclockwise direction. Our terminal side will be in the fourth quadrant of the coordinate plane. And it looks like that. So we're rotating counterclockwise. For negative 110 degrees, we are going to move in a clockwise direction. Terminal side will move almost halfway around. We're actually just out past 90 degrees on the lower part of this coordinate plane. 990 degrees will require more than one rotation. It's positive, so it'll be rotating counterclockwise. And we can see from there 360 twice is 720, so it looks like we have something that's roughly 270 degrees. Not quite 3 rotations around the origin. This is your opportunity to try to draw these angles in standard position. Pause the video and resume when you're ready to check your work. Okay, for 210 degrees, a positive angle will rotate counterclockwise, and this will take us over halfway and into the third quadrant. 1020. Also a positive angle will be rotating counterclockwise 1020, which is more than one rotation, more than two rotations, but not quite three rotations. So when we look at this one, we go from the positive x-axis around once, around twice, and the remaining 300 degrees puts us into the fourth quadrant. Our last one is a negative 300 degrees. We're going to rotate clockwise and find that our terminal side ends up in quadrant 1, just past 90 degrees. When we're talking about coterminal angles, we're talking about the terminal side being in the same place as a number of different angles. For instance, in this picture, 120 degrees has a terminal side in the second quadrant, whereas negative 240 degree angle also has exactly that same position for its terminal side. Given that they both land with the terminal side in exactly the same position, we call them coterminal angles. In addition to having these two angles, you have an infinite number of angles that will land with the same terminal side in the position where you see this one. And that would be any angle with multiple rotations that land in this spot. They could be either positive angles or negative angles. And this is what we're talking about here, infinitely many coterminal angles. We're going to find the measures of a positive angle and a negative angle that are coterminal with each of our given angles. First, we might add 360 degrees to find a positive coterminal angle, and then subtract 360 degrees to find a negative coterminal angle. When we add 360 degrees, we get 425, and when we subtract, we get 295, negative 295. That would make both of these angle measures coterminal with our theta equaling 65 degrees. Drawing a picture is an extremely helpful tool in setting this up if you have difficulty visualizing adding or subtracting 360 degrees. Our second one, 410 degrees, our standard protocol. In this case, since it's already over 360 degrees, we can find a positive coterminal angle by subtracting 360 degrees to give us 50 degrees. And then we can go ahead and subtract it again to give us a negative coterminal angle. So we end up 410 would be found in the second quadrant at 50 degrees. If we rotate around the opposite direction, that would be 310. That's our negative angle, negative 310. And over here, we have the answer indicated. It's your opportunity now to find a positive angle and a negative angle that are coterminal with this theta of 88 degrees. We'll have other examples on the next couple pages. Pause the video, resume when you're ready to check your work. Okay, first thing we do to find a positive one would be to add 360 degrees to find the positive one, and we end up with 448 degrees. To find the negative, we could subtract 360 degrees, and we end up with negative 272 degrees as coterminal with 88 degrees. On the next page, find positive and negative angles that are coterminal with 500. Resume when you're ready to check your work. Subtracting 360 degrees, we can find a positive coterminal angle. Since 500 is greater than 360, we end up with, we're adding 360 degrees, we end up with 860. And subtracting 360 degrees, we subtracted a multiple of that so that we could go to a lower degree value here, so that it's only a single rotation. We subtracted a multiple of 360. 220 degrees and 860 and 500 all fall into the same coterminal angles with the terminal side in the same spot. Last one, find the measure of the positive angle and a negative angle that are coterminal with negative 120 degrees. Pause the video. Resume when you're ready to check your work. Adding 360 degrees, we'll be able to find a positive coterminal angle. Gives us 240 degrees. And then if we subtract 360 degrees from the original negative 120, we'll end up with negative 480 degrees as a negative coterminal angle. And this would be more than one rotation around in order to make that second negative angle. These two angles are then coterminal with negative 120 degrees. There's a couple more details we need to learn as we're moving through angles of rotation. In standard position, an angle is formed with its initial side along the x-axis and its terminal side at the completion of its rotation. From that terminal side, we have another angle that could be discussed, and that angle is called the reference angle. That reference angle is found by creating an angle between the terminal side and the closest x-axis. In other words, you might consider dropping a perpendicular line from that terminal side directly down to the x-axis to help you determine where you're going to find this angle. Later on, we're going to talk about using reference angles for angles that measure greater than 90 degrees or less than 0. When you're looking at these, it helps to have a coordinate plane across your angle, and this angle is going from the red axis. It's got its initial side on the positive x-axis, and rotating around. This black line here is its terminal side, and our angle measure is 135. To find the reference angle, we would be looking for the angle that falls from the terminal side to the closest x-axis. We know that half a rotation is 180, so 180 minus 135 would give us our reference angle for letter A. And that angle measure is 45 degrees. As a similar scenario, with our theta equaling negative 105, going clockwise here to our terminal side, we would look for our reference angle to be between the negative x-axis over here and our terminal side. Also remembering that this amount is 180 degrees, we find that that reference angle is 75 degrees. Now it doesn't have a negative connotation related to this. It is just the measurement of an angle between the terminal side and the x-axis. In our last example, we have rotated all the way around in the positive direction 325 degrees. Our reference angle is found between our terminal side and our x-axis over here, so the closest x-axis. Right there. And being that this is 325 degrees, we can take away from 360 to determine that our measure for this angle, the remaining measure is 35 degrees. It's your opportunity now. Check each of these angles and determine the measure of the reference angle for each one. Pause the video. Resume when you're ready to determine your answer. For 105 degrees, just past 90 degrees. The measure of that reference angle is 75. We find that from the terminal side down to the x-axis at 75 degrees. And on our other one, the measure of this is 65 degrees. We have that measure right here between the x-axis and our terminal side. Our last one, 310 degrees. Pause the video, resume when you're ready to check your answer. Okay, this angle is found between the terminal side and our x-axis here. 310 degrees around this way leaves us with only 50 degrees as our reference angle between the terminal side and the x-axis. Now that we've adjusted to putting an angle on a coordinate plane in standard position, which is a quick reminder, we have standard position as the initial side along the positive x-axis, and our terminal side indicates where the rotation has completed. Our theta is how far the rotation occurred from 0 around in a counterclockwise manner for positive, in a clockwise manner for negative angles. We're now going to look at how we configure our trigonometric functions for any angle in standard position. The first step is to select a point, and many times you'll be given a point with coordinates on the terminal side. So here's our point right here. We then have to determine what our R is. R is like our hypotenuse in a right triangle. What we've done is we've dropped a perpendicular line from the point to our x-axis. We have a right angle here. This R is our hypotenuse. As you consider that when we rotate around and have the same distance from here, you might also consider that radius. I think that's where we get our R from. The distance R from point P to the origin along this line here is given by our distance formula. Square root of x squared plus y squared. So we're going to take our x and y values, square each of them, add them, and take their square root to find out what R is. Our trig functions are found by understanding something about that relationship. And let's go back just for, well, we'll look at that later. Our relationship here, when we look at the sine of theta, our opposite side when we're in a coordinate plane is our y-coordinate, and our hypotenuse is that r value or the radius as we're rotating around the coordinate plane. In cosine, our adjacent side on a right triangle is equal to the x-coordinate. Again, our r is the hypotenuse. And tangent takes that opposite side, which is a y value, and our adjacent side, which is our x value, to help us figure out those trigonometric functions when we have an angle of rotation. So here you can kind of see our picture again. Okay, for angles of rotation in our example number 4, we're going to find values of our trigonometric functions. We have a point, -6, 9, on the terminal side of our theta that's in standard position. We want to find the exact values of the 6 trigonometric functions for theta. We've got the point, and we're going to use that point to help us sketch a right triangle and the angle that is in standard position. Our first step then, after we've got that point there, we've created our triangle, and this is the one I want to emphasize that we're using. We're using the triangle that's here only. We're never ever going to use this one that shows up there. We'll only use the one that is down below, as you see below the terminal side here with the reference angle. That's why we went through the whole steps to find reference angle, because this angle is really important for what we're doing here. We'll never use this one that is its side on the y-axis. So first we want to find R. We have our point P, and we're going to use the distance formula to help us find our value for r, which is right here along the terminal side. So r is here. If we look, our y distance, we go up from 0 to the top, this distance is 9, that's equal to y. And if we take across the base here, or the bottom, this value is our x value. This will help us determine our trig ratios that we're going to be using. Here in our reference angle is our theta that we're using to help us figure out our different ratios. So we can see across from theta is y, so that's opposite. That's for our sine over the hypotenuse, and adjacent to theta is x. And this is how we get our ratio for cosine. So moving to the next page, we're going to see that we're going to set up each of our ratios. If we take our sine theta is y over r, our cosine theta is x over r, and our tangent theta is y over x, we're going to replace each of these with the values that we got from the previous slide. Our y is equal to 9, our x is negative 6, and our radius was given to us when we found from the distance formula of 3 square root of 13. So we've plugged each of these in. At the moment, they all need a little bit of work. So when we're looking at denominators that have radicals in them, we do want to remember that we rationalize our denominator by multiplying by the square root of 13, numerator and denominator, and we will then simplify. 9 divided by 3 gives us 3. Over here with the cosine, multiply by the square root of 3, divide by 3, and we end up negative 2 root 3 over 13. And in tangent, we do have to simplify by dividing both numerator and denominator by 3. When we move over to the next page, we're now going to find the other 3 trigonometric functions, given that they are reciprocals of our cosine, sine, and sine. And we need to start associating these pairs. If you remember from 13.1, each of the functions is paired with another one, and in the case of the two paired names, only one of them has a co in it. So given that this is cosecant, it would have to go with sine. Secant would then also go with cosine here, and cotangent is associated or paired with tangent. What we do with each of these is then flip over the results we got from the previous page. You'll notice that they look a little different than what we had before because there was no requirement to take the denominator and rationalize it. On our next page, we do want to remember that our r is a distance and therefore will always be positive regardless of whatever is going on with x and y. And our x and y will have the sign associated with their quadrant where you're going to be drawing your triangle. So that's one way of remembering what you're working with. On this side, you have an opportunity to take a point on the terminal side of theta and find the exact values of the 6 trigonometric functions for our theta. Pause the video and resume when you're ready to check your work. As we did previously, we have plotted the point. We have sketched a right triangle by dropping a perpendicular line down to the x-axis. We have a right angle there. Our theta that is being used for trig functions is here in the reference angle in the corner. And it's nice that in this case we didn't draw that other line across to the y-axis to confuse us. Just remember that the triangle is only the one that's got the short side on the x-axis there. Our angle theta is in standard position, and our first step is to find r. Given the distance formula, we now have solved it to give us 3 square root of 5 as our r value. And we need each of these values, x equaling negative 3, y equaling 6, and r equaling 3 root 5 in order to calculate the rest of our values. Our sine theta, y over r, cosine x over r, and tangent y over x. Plugging values in, we have 6 over 3 root 5 negative 3 over 3 root 5, and negative 6 over 3. Our sine and cosine ratios do need to be rationalized by multiplying by the square root of 5 and reducing by dividing by 2, which gives us the answer for sine theta, this answer for cosine theta, and this answer for tangent. You will notice that due to that angle being in the second quadrant, cosine and tangent are both negative, whereas sine is still positive. Using the reciprocals to find our cosecant and secant and cotangent, cosecant with sine, secant with cosine, and cotangent with tangent gives us the following ratios as their reciprocals. Again, no need to rationalize any denominators on this side. That completes this portion of our introduction to trigonometry. Take out your study guide, finish the problems in there, and make sure you ask questions on anything that you didn't understand when you come to class.